I'm going to start by drawing a dot to represent the box. When I draw that dot, I recognize that there are arrows I can draw on the dot that will help me determine the forces that are acting on the system. So I will draw one force. What am I drawing an arrow for? Is the box in contact with any surface? It sure is. So I will draw another arrow representing the force from the surface on the box. Is the box experiencing any resistive force? Yes. There's an indication that there's friction. Friction opposes the direction of motion. I'll draw another arrow that indicates friction. All right, I have drawn my free body diagram. If these forces are unbalanced, then the object will accelerate. If they're not unbalanced, the object won't accelerate. But I'm being asked to find the velocity, so I think the object's going to accelerate. So I'm going to treat this as a Newton's second law problem. I'm required to now put together a coordinate system, and I have choices on the coordinate system I can use. I can align my coordinate system with any force I'd like or in any way I'd like, but I was given some directives that the best way to do a problem like this would be to align the coordinate system with the direction of the acceleration first, and if that doesn't work, align it with the most number of forces possible to reduce how much work there is. I'm going to align it with the direction of the acceleration, and that would be along this line. And when I do that, that means that the x direction will be along, the y direction will be along this line. That's going to be my coordinate system that I'm going to use for this particular problem. Now that I've done that, I will notice that I have an off-axis force. Because I have an off-axis force, I'll have to break that force up into its component vectors. I need to make those component vectors aligned with the coordinate system I've chosen. I'm going to choose a set of coordinate vectors that's like this and like that. And my angle for my ramp is here. I'm not going to go into why that's true. If you don't remember that, at least, there's some things you can look up. I'm also not going to show you where sine and cosine come from. That was also a first semester skill that I hoped wasn't even my thing, but I taught it to you anyways. But it's going to be mg sine theta to go with that component and mg cosine theta to go with that component. That's just because adjacent and opposite, that's the way that works. But you probably should go back and work that out for yourself if you don't remember, but we already did that. We did all of this. But once I have those, I can go ahead and employ Newton's laws. I will say net force in the y direction equals 0. And net force in the x direction equals ma, right? This is a set of instructions. And in this set of instructions, I'm supposed to take all the forces that are in that particular direction and set them equal to 0 or ma. So in the y direction, I believe I have two forces, normal force upwards and a portion of the weight downwards. So normal minus mg cosine theta equals 0. Done. Now I'll go on to the next ones. I have two forces. I have mg sine theta minus friction equals 0. Equals ma. All right, I have used Newton's laws. Those laws gave me a set of directions, or at least a set of equations that I might be able to use to solve for my problem. Forces are very good at telling me an acceleration or the size of an individual force. I want the acceleration. However, I don't know the size of the frictional force yet, but I think I have a way to get it because I know friction is defined as mu times the normal force, all of which is on your equation sheet. So now that I have that, I believe there are some substitutions I can do. In fact, first thing I'm going to notice that normal force equals mg cosine theta, something I told you should memorize. Why? Because every single inclined plane does this exact thing every time. Worth memorizing, because it's going to come up. We have lots of ramps in our lives. So you should memorize it. In fact, I'm going to be very clear about what I'm about to say next. I'm giving you a quiz tomorrow. This might appear on it. I said for you to memorize it first semester. You didn't. You should. So now we might start doing just this. I would give you a bunch of practice on my AP if I thought that you would authentically do it. I'm still going to give you a bunch of practice on my AP because you need the review. I do it every year. That's not new. But I do want to offer you that if you want to pass the AP exam and you can't do this problem, you have work to do. That's all I'm saying, and I'm not trying to guilt you. This might be on the exam. There's going to be 5 FRQs. This was a big part of first semester. It's not unreasonable to expect this to be on the exam. If you want to pass it, you have to understand this problem. I know that I throw a lot of equations and theory at you. That is physics. I'll put more examples in your hands too, but at the same time, we got to do this kind of stuff. Do you see where to go next? I hope so. I'm going to substitute this here and then substitute this here. I think I can do 2 steps at once, but I'm not sure, so I'm not going to. I'm going to say that this equals mu mg cosine theta. That's my first substitution. And my second substitution will be mg sine theta minus friction, which is mu mg cosine theta equals ma. The second thing I think you should memorize is this. This is the part of the weight that's down a ramp. It will be like this every single time. And if you memorize it, at least you'll memorize something that works on ramps. You can work it out, but working this out takes time. You understand? There's no need to work it out if it's going to be a standard ramp question. This is a standard ramp question. All right, I can solve for A. I know mu, I know m, I know g, and I know theta. So you should do so. And that's just pushing buttons. So it's 1.5 meters per second squared. That's not the end of this. That gives us the acceleration. And we know that delta x is 3 meters. We know the initial velocity is 0, and I wanted the final velocity. And plug it in, get an equation. Look, there's other ways to do this. I did indicate that you could calculate the work done by friction. That would work. You could do that, figure out how much energy was taken out of the system due to friction. This would be friction times delta x times the cosine of 180. You could do it this way too. We learned this as well. We learned alternative ways to do things. But again, I don't know how many of these things you remember, but this one clearly 0%. So we've done it again. Yeah? So in this, in the problem we're talking about here, would the disc or the ring make it to the bottom first? And your first question should be, well, if there's no friction, they would slide the same. In fact, it wouldn't even matter what their mass is. They'd slide the same way and make it down to the bottom first. The only reason this problem becomes relevant to us is if there's enough friction for them to roll without slipping. That's the relevant question. Remember, those are the phrasings, too, that I want you to have. Is the object going to roll without slipping? If they are, well, that changes the question. Now, we know the answer, because we talked about the answer, and you saw it performed in front of you. Which one makes it down to the bottom first, the disc or the ring? Can you explain why? Without using equations, can you explain why? It's a lot of whispering. Anybody want to be bold and just say it loud with voice like I do? Go ahead.
The ring has a greater inertia, so it's harder to move.
The ring has greater inertia, so it's harder to move. Done. Right? Isn't that really what we want to say? Now, we could go further. We could use vocabulary. Inertia is good, so I think that's great. Moment of inertia may be better because we know that's the actual phrasing, but I think inertia is just fine. The disc is easier to turn than the ring, so the disc will go faster. Right? I'd probably have to say something about being acted on by the same forces, right? Same force of gravity, all that kind of stuff. But under those circumstances, the idea here is that it's easier to turn the disc than it is to turn the ring. Now we can do the math. Yesterday we learned how to do the math, remember? So do we understand that at the top, if they are the same mass, they have the same amount of energy at the top of the ramp? I don't know that you know that, but you should. Because at the top of the ramp, they're not moving. Their energy will be solely based on how high they are above the reference level and what their mass is. So they have the same mass, regardless of their shape. If I put them both at the same height, they should have the same amount of gravitational potential energy. Do they have the same amount of energy at the bottom when they're rolling? Will the disc have the same energy as the ring? Have to be. That energy came from here. So they would have to have the same amount of energy at the bottom since they both started with the same amount of energy. At the bottom, that energy gets divided up, with some of the energy being associated with the motion of its center of mass. I'm saying that's complicated, but some of that energy is associated with how fast it's moving, how fast it's changing location. And some of that energy is associated with how fast it's spinning. Right? So we take the same amount of energy and we divide it up in two places. And although they both have the same translational inertia, that's m. M is their translational inertia, the amount of inertia to move it from one place to another. They have different rotational inertias. Now, we figured out in our discussion yesterday that if it's rolling, well, let's stick with my color coding here. If it's rolling, although we will say the kinetic energy is 1/2 mv squared, we might do some stuff to the rotational kinetic energy to make all of our variables kind of work out easier, right? Put everything in terms of the linear velocity so that we can figure out how fast it's actually moving from place to place. So instead of talking about how fast it's spinning, we'll use the fact that it's rolling to do a substitution. Now, I left this out because I is different for one thing than the other, right? I'm either going to put mr squared here or 1/2 mr squared here, since we're talking about the difference between a disk or a ring. Now, it looks clear to me, just in this, without putting any numbers in, that less of that energy is going to have to go into the rotational one for the disk, because of that 1/2 that's there. When I work this out and get the share for a ring, this is going to look like mgh equals 1/2 mv squared plus 1/2 mr squared times v over r squared.
Good morning again. At this time, we're going to release for Orange Club, but we have 2 cancellations, so please pay attention.
So you see, if we're dealing with the disk, it looks like the energy has to be split up 50-50, right? I'm sorry, dealing with the ring. The energy has to be split up 50-50, right? Half of the energy will be in translational and half of the energy will be in rotational, because the 1/2s are the same. But for the disk, it's not split up evenly, right? More of the energy will get to stay with translational, and less of it will have to go for rotational. Working this out, do you notice the R's cancel? And the M's will eventually cancel too. All righty. So here's the circumstance I'd like to bring up. Consider a situation in which we have a lead up to the ramp. Something like that. And we give them both the same velocity. So they're spinning at the same speed and they're moving at the same speed. And I roll them both and they're approaching the ramp. Everybody got this kind of in your mind? So they're rolling and they're moving towards the bottom of the ramp and they're at the same speed. Do they have the same energy? I am not trying to confuse you. I would not jump at the answer. I would think it through. So again, I take both, and I'm not arbitrary. I mean, we're talking about this, right? If we think about the ring and think about the disk, when they're rolling, 1/2 mv squared will be the same for both, right? But we're adding 1/2 I omega squared to both. Now we're talking about rolling them at the same speed. So omega is the same and the v's are the same. You guys follow me up to this point? That means this part is the same for both. Is this part the same for both? Now, what I'm trying to say that they do not have the same energy, right? The one that is harder to turn has more energy because it takes, and this is you guys think that I'm just saying these words? No, I'm trying to give you the vocabulary you have to say. So these two objects have the same kinetic energy because their velocity is the same and their mass is the same. They have different rotational kinetic energies because their moment of inertias aren't the same, but their angular velocity is the same. That's why the ring has more energy than the disk, because the rotational part requires more energy to get to the same speed as the disk. Now, the word I want you to use here is more work was done. The word work means change in kinetic energy. So when we talk about which one of these requires more work, it's going to be the ring. That's important for something I'm going to say in a few minutes. But the ring requires more work to get up to the same speed as the disk. Now, this next part I think is hard. I don't think what we just talked about here is hard. But I think the next part will be. Because you do understand that on a test, they're going to play with this a little bit. Now, which one of these will go higher up on the ramp? If they're both rolled at the same speed, which one will go higher up on the ramp? What's that? See, we're still having trouble. Which one has more energy? The ring. When it stops on the ramp, what kind of energy will it have? Gravitational potential, right? So let's just talk about the disk for a moment. The disk is eventually going to make it up to up somewhere on the ramp, right? So right now it's got some velocity. When it makes it up here, all the velocity is done, right? It stopped. What kind of energy does it have? Gravitational, MGH. So isn't it clear that how high it makes it, or how far it makes it along the ramp, is going to be based on how much energy it has? Which one has more energy? The disk or the ring? So the ring is going to make it higher up on the ramp because it has more energy. Now let's make it tricky. Do you want a tricky question? What if the ramp is slippery? So I roll them both towards the ramp, but the ramp is slippery. What won't change about these two things? By saying slippery, I'm saying that's exactly, okay, who said it? All right, there's no friction. So if there's no friction acting on this, which of the things won't change? Right? We have two things to talk about here, right? We have kinetic energy and rotational kinetic energy. If there's no friction, will the object still go up the ramp? Yeah. Will its rotational speed change? What would stop it? What forces are acting on the object as it's going up the ramp? Weight, sure. Acts at the center. And normal force acts that way. Can either of those cause a torque about the middle? Do you see how the weight acts at the middle? It can't apply a torque. And the normal force is pointed at the middle, so it can't apply a torque. So there's no force here to change how fast it's spinning. So it'll make it to its highest point, but it'll still be spinning. Right? There's nothing to stop it from spinning. It goes up the ramp because the normal force is pushing it upwards. But it won't ever change its spin. Since both of them have the same amount of translational kinetic energy, they'll go to whatever height will allow that energy to become gravitational potential energy. But they will still have kinetic energy because they're still spinning. In fact, the harder question to ask is, if the ramp has friction, will they go higher or lower than a ramp that doesn't have friction? Now, the answer's in front of you, but I think this is a really hard question. Do you want me to state it again? I want you to think through. Here, listen closely. If there's no friction on the ramp, clearly we need to come back to this on Monday.